Before I talked about these very standard, tasks and data sets, and we're trying to build like this representation learning for doing well on those. And in this part of the talk, I'm gonna like dream a little bit more and try and do some more semantic tasks. So this stuff isn't really quite as polished, but I don't know, maybe it gives some more ideas of sort of things we could do in the future. So what we tried to do was link text to something that's happening in the world. So with the idea that the way humans learn language is to use it in the world, right? It's kind of useless without communicating something we're actually gonna do. So that's kind of called grounding, when you try and link language to something like physical in the universe. So most of natural language processing research, if you look at the papers from the last 10 years, don't really look at situated learning. They're just looking at sort of language in a vacuum. So you've got all these tasks like I just talked about, part of speech and chunking and parsing and machines translation, summarization, and so on. But we kind of understand language given the world and our knowledge about the world. So there's just some sentences here, like John saw Bill in the park with his telescope. This is kind of a classic sentence where you're trying to resolve whether the telescope is linked to Bill or John. And you might already have some world knowledge, like Bill owned a telescope. It's kind of stupid, but if you did, then disambiguating the sentence is much easier. And there's a couple more examples there. John went to the bank, like you might know it's a river bank due to some other knowledge you have about the world. And like he passed the exam, okay, it's kind of like impossible to ground what exactly he is in this sentence without any external knowledge, but you might have it already. I was thinking, like a stupid example, but you're in a concert and you're watching a band, and like your friend says to you, he's a really good drummer. And well, he's a he, right? It could be anyone, but it's kind of obvious to you, given your situation of where you are, who they're talking about, right? So how can we kind of put this stuff into our neural network, basically, somehow? And here's just some really sort of toy, simple ways of doing it. So we want to try and learn like language in a situated environment. So we want to have like characters and objects and language associated with them. So if you want to do this like really properly, it's in our world, then you have to deal with all kinds of things like vision and speech and motor control, like for a robot or something, as well as the language understanding. But in a multi-user game environment, it might be much easier to do this. So there's like very complicated actually like computer games right now with really nice graphics and stuff. So you could imagine like a quite nice simulation where you could try and ground language in that game. I'm not going to do that and do something really, really stupid here, where I have just like a very simple text adventure game, like going back to these old text adventure games. In the text adventure game, I'm going to use that as a kind of test bed for machine learning, where you have physical objects and atomic actions. So things like get, move, give, shoot, and character 1, key 2. These would be kind of like the grounded concepts in the game that are like linked to the simulation itself. So they're not linked to language. But then you can imagine like language utterances that in that world which are linked to those concepts. So these are just kind of like tokens that you would ground language to. So we kind of defined this task called the concept labeling task, where you have to, similar to all those word tagging tasks I showed before. Now we're going to tag the words with concepts from the universe of possible concepts in our world. Okay, and so we're kind of like word sense disambiguation in a way, but actually tied to a particular universe. So you might know, for example, there's 2 particular cartons of milk in the house or something, and that, so you're actually labeling the word with one of those. So sort of that's different to word sense disambiguation, right, where you're not actually talking about a physical entity of a carton of milk. So maybe I'll just cut to this example to make it clear. So you have the way I'm going to represent it is just this universe U of a set of concepts. So these are all the concepts in the world. They're not language. I've put like these arrows just to say that's a concept, like mark and garden, and then you have edges that describe the relationship between those concepts in the world. So mark has location, garden, for example. So you can build this kind of graph that describes the universe. So the idea then is, given a sentence like he cooks the rice, to predict the concept labels. So that's these things. And each one of these tags is going to be one of the nodes in this graph, okay? And you're given both X and U, so both the sentence and the universe, to try and solve the task of predicting Y. So the idea is that you can use the universe to get much better prediction accuracy, because you can use kind of this world knowledge of like who is where, who's carrying what, and so on. So this is kind of like the setup. So yeah, I think this slide just says the same thing. Basically, but we're gonna train a model with these training triples. So X, Y, and U. So so X is the input text, Y is the output, and U is the universe. So U is also changing, by the way. So these edges, so if somebody changes location, then these edges are going to change, right? So that thing is changing over time. So that's sort of different to using something like WordNet, which is kind of like, just a fixed graph of concepts. That something like WordNet tells you things like a car has part wheel, okay, but it's kind of like fixed. It doesn't tell you like the locations of actual people who are moving around. So that's kind of a little bit different. So how could you use the universe to improve your concept labeling? And this is just an example with he cooks the rice. So it's basically here, given this very simple universe, the cooks the rice are all very easy. They're basically unambiguous. So, because there's only one concept rice and there's only one concept cook, and we just use this kind of empty concept to label words that you can't ground with a physical entity. So you can do those three, but then the he is the tricky one. So there's kind of 2 implicit rules that you need to use given that particular universe in order to give the correct label. So one implicit rule is that he is picking out a subset of the concepts. So it's probably either John or Mark and not Gina. So you would have had to have learned that over time, over training data, that Gina is normally referred to with she. And so that's one of the things, but there's still two possibilities, right? So then the second thing that you could use from the universe is that, if you go back, that John has location kitchen, he's in the kitchen, and the rice is also in the kitchen. So this makes, these two pieces of information make it more likely to label that concept he with John. So we want to kind of like make a model that can learn these kind of rules, like all implicitly, so just learn the representations to be able to do this stuff. And so it could handle all kinds of sentences, like here's some examples. He picked up the hat there, the milk on the table, she left the kitchen, Mark drinks the orange. So the ones I've like bolded are the kind of ones that are a bit more ambiguous, and you might need to use some world knowledge how to resolve them. So we're going to try and do that. So the simplest kind of model you could choose to do that would be like a kind of structured output learning kind of model, where you you define for any given set of possible concept labels y a scoring function. So given a scoring function g, that given x and u, which you know, and that particular y, it gives a score, and then you just find the maximum scoring set of labels, right? This kind of like a high level kind of model that you could choose. Of course, you have to choose what exactly is inside G, but we could learn that kind of thing on training data. So yeah, you do have a problem that the argmax might be slow to compute depending on how you do it, but so we're going to make some training data. So we wrote a little text adventure game, like I was saying, and so basically the simulation runs by generating new events, like somebody going somewhere, somebody picking up an object, or giving an object to another person, and so on. And so those kind of things happening in the simulation where basically the universe graph is changing. And then we need to generate for any given event some text that would be like the natural language text that describes the event. And then we need to update the universe and repeat. So this is kind of the simulation that we did. And then we can get, basically, we made this very small thing with just 58 concepts, 15 verbs, 10 actors, and 15 objects and 6 rooms. So kind of like a house with a family doing stuff. And then we've got these kind of sentences. The father gets some yogurt from the sideboard. He sits on the chair. And so this is the training set. But then you have this universe, what we call the universe, just this graph, for every one of these pairs as well. So we try just SVM struct. So with that argmax thing that I showed, just using the raw words and concept relations as input. So pretty naive just to start. And we got these kind of results. So this is the percentage error rate on a per concept basis, I think, or is it on the, oh no, it might be on the whole sentence, whether you got the whole sentence correctly labeled with all the concepts. So, but already we had one nice thing that basically if we added the universe graph as features, then we get better results. It goes from 40%, which is pretty bad, down to 20%. So it does help. So then we were like, okay, can we make a kind of feature learning model that does better, basically? Can we learn some hidden representations? So So yeah, we tried to do that, and we took this kind of model. It's more of these embedding text models, just like in all the talks I've given before. And so, but it's sort of formed of these two parts. So the G function that scores the sentence X, the universe U, and for a particular labeling set Y is formulated like this. It's two parts where on the left-hand side, we take the score of the, well, not a score, we generate an embedding representation for all the tags apart from the ith tag, okay, apart from one of the tags. And on the right-hand side, we generate a representation for the ith concept together with all the information about it that's in the universe. And then we take the dot product of those two. So it's kind of like, is this predicting this one particular concept for one word in the sentence consistent with predicting with all the concepts predicted for the other words in the sentence? And we sum over all the possible concepts in the sentence. So that's kind of the scoring function. But I have a pictorial representation which maybe helps. So we do that with a sliding window over each word. So here you have, so this was the left-hand side, the G minus I function. So we have like the words, and then you have like the concepts that you've already labeled, apart from the missing one here. That's the question mark. And so then we have like lookup tables, just like before, for the words, and we also have lookup tables for the concepts. So we're going to learn all those vector representations, concatenate them all together, and then have just some linear matrix that squashes them back to some n-dimensional representation. And then on the right hand side, that was the this thing, that HYIU. We have the missing concept plus all its relations in the database. So for example, we have John plus the location he's in, the things he's contained by, or the things he's carrying, like all those things would be along there as features. And then that thing, there's also lookup tables for all the concepts, just like there. So we can generate those lookup tables, map to an n-dimensional space, just like on the left-hand side, and then do a dot product between them. And that's the score for that concept. And then we sum that thing over all the positions. So that's kind of the network that we learn. But we still need kind of an inference algorithm to do like the argmax. So the way we chose to do it was a lot like the learning as search optimization algorithm by Hal Dalmay and collaborators. I'm not sure if you know it, but it basically you choose like a particular search algorithm that you're going to use during inference, and then you train your model's parameters to be good at that particular search algorithm. So the particular search algorithm we chose was, we start with all positions unlabeled, and then we look at what the score would be for every possible concept in every position, and we select the position and concept that we have the most confidence in our model, so it's the highest scoring. We accept that, kind of greedily, remove that position from the set of available ones because it's fixed, and then we go back and find the next one that we're most confident in. And so what you hope, and it's going to learn how to choose, the confidences so that this search algorithm works well. So what you hope it will do during training is choose the least ambiguous concepts to label first. So, for example, in that example, the cooks the rice, you hope it labels these first, and then leaves that one till last. And then if it leaves that one till last, then it's good, because when you're trying to label that one, you have all the information that this he is something to do with, it's something to do with these three concepts. And you know that those three concepts, you know information about them, like the rice is in the kitchen, okay? So that's why it can work, because then we have this information here, rice is in the kitchen, as part of the input to the network. So it can basically, look, there's a sort of trivial match here, that there's kitchen here and kitchen here, that you could imagine, it can learn to sort of latch onto those kind of things and say, okay, this all the concepts that we've predicted for this sentence are consistent somehow, semantically consistent. If that's a good thing to do. I mean, if depending on say the verb that's in the sentence, it might be good to choose things inconsistent. I don't know. So hopefully it's learning those things from the training data. So yeah, so we tried that whole thing, and it's working quite well on that simulated data. So this is this neural network. This was the SVM struct method, and this is this neural network where we provide different kinds of information. If we only provide the words, so not the universe, we get like 35%. If we add contained by information, so you know which object is contained by which other object, then you can disambiguate more concepts. You go down to 17%. If you only include the location information, you get 5%, and you get almost perfect results if you include both of these things. So these were in the simulation, these are the only two types of universe information. So basically it's just a sort of proof of concept they can learn from that kind of data. So, the challenge would be to make that thing work on more realistic data. So it's kind of tricky to get hold of that data, but so what I'm going to do in the next part of the talk is just use WordNet instead, and try and do more large scale, more realistic things with the same kind of flavor but with WordNet. And this was just to say that again it's learning like interesting embedding representations, like it learns football and toy and video game are similar, and it learns the females and the males are like close in the embedding space, because it needs that for the he-she type disambiguation and stuff like that. So yeah, so that's a pretty simple approach that is on toy data, but tries to show how you can use this world knowledge. So now I'm going to switch to a similar thing, but on kind of more real data. So here it is. The date here is wrong, because I've stolen these slides from Antoine Board, who's one of my collaborators. So this is about doing the same kind of disambiguation, but using like a large-scale knowledge base instead of this like toy data. So what kind of knowledge bases are there out there? There's things like Psych, you pronounce that Psych, WordNet and Freebase, which have like millions of facts, or WordNet has 200,000 plus words, Freebase has 360 million facts. So these are kind of like more large-scale world knowledge that we could try and train on one of these networks on. So I'm just going to skip that. And yeah, we're going to use the same kind of tricks. Basically, we're going to represent the elements of these knowledge bases in a low-dimensional embedding space and try and capture the relations between them in the graph, which looks just like that universe graph that I had before in the toy setting. I don't know if I need to skip this because it's basically the same stuff. I just cut to WordNet basically. So WordNet has kind of 18 relation types. So they look like this. So like I was saying, you have things like door, has part, lock, brain, hypernym, neural structure. So it's, and auto, hypernym, SUV. So you have this kind of class information about entities and also part information about physical pieces of things. So it tells you lots of things about the world. So there's 41,000 entities in the data set that we chose. It's quite a large subset of WordNet, I think. So we're basically going to train like the concept embeddings for that graph, and we do that with this similar energy-based model. So if you take those triples, like door, has, part, lock, we want to basically learn the embeddings for all of those concept entities such that it can remember kind of those triples, and also would generalize to triples not in the data set, right? So there's all kinds of things that have been missed out, like you could think of, the graph has missing edges, so you can generalize to these. And so we can check that by removing some of the triples from WordNet and seeing if we could predict them. So this way we can see whether we're kind of capturing the graph. So we use this as a kind of pre-training, if you like, for other tasks. So we just do that with a simple little neural network that takes the triple, the left-hand side, the relation, the right-hand side, and has two modules that take. So the first module takes the left-hand side component and the relation and produces an embedding, and the right-hand side does the same thing. And then we basically want the dot product of those two, or some other function. If you don't want to use a dot product, we just call it H here, to give a high score to things that are in the database and a low score to things that aren't, just like all the other stuff we've done before. We tried different parameterizations of these G functions. So you could take a linear layer or like some non-linearities in there as well, and then you can use a ranking loss, just like we did before as well. So you take one of the examples in the database, like a true example, and that should be like should have a higher score than a randomly generated negative example. So just like we did with pre-training the language model before, we could replace either the left-hand side of the relation or the right-hand side with some random concept, and then the neural network should get a lower score for that thing. And so notice the thing isn't symmetric as well. I mean, because you've got something like car has part wheel, it's not true that wheel has part car, right? So you need the definition of this network has to take account of that. That's sort of why you might want to have a different, module G left to G right, okay, so that it can do that. So we just trained that with a ranking loss, can look at how well that does on the test set of triples that we left out by basically seeing where the true one would be, but if we rank them all. And well, this graph just shows, it learns something. I don't know, compared to some stupid baselines of like just taking bigram counts or something like that. And yeah, so then we can plot the embeddings of the word entities. And as before, you get some nice things like all the cities are close together. I can't hardly even see them. Buenos Aires, Sarajevo is there. And battles are together, and rivers are together, and stuff like that. And so on. So there's all kinds of clusters of concepts in this database. For some reason, computers are near religion. So I don't know what that says about what you're doing. And yeah, so that's kind of the pre-training thing that we do. Sorry, that was all just to show what we're going to do to learn the database, to actually use that for something real. So now we get back to the semantic task that we're interested in trying to work on, to try and get something a bit more semantic than we had with those, like, just those simple tagging tasks from the first part of the talk. So now we've got this database and we've kind of encoded it in a neural network. We can do things with it, right? So now we have these representations. We can use them to try and predict some end task. So kind of, a semantic end task that you might be interested in is called semantic parsing, which is basically like semantic role labeling. Here, I'll just go to here. So semantic role labeling that I talked about before would get you things like you would know that the predicate accompanies has like an arg0 musical score and arg1 television program, right? But it doesn't get you to the final grounding of those words to WordNet, to a database, which is what you'd want to do in a full like semantic parsing system. So this basically is the link between using the universe stuff from the simulation that I was talking about, and the semantic role labeling from the earlier talk, right? Because if you kind of combine those things together with some real world data, you can kind of ground, like have an input sentence like that, a musical score accompanies a television program, and kind of turn it into a logical form that grounds it to a database, WordNet in this case. So, and you basically do that by using these steps. You use the semantic role labeling to break it into triples. Then you, that's what we do. We pre-process those phrases with part of speech and chunking, so that you can know that, say, score is a noun here and accompany is a verb, but you still don't know which element in the WordNet database that is, because there could be multiple senses. Okay, so what you basically have to do in this final step is where you can either call it concept grounding to the WordNet database, or just word sense disambiguation. So we've put this number 1 here to denote that even if you know something in a word is like a company and its part of speech is VB, the 1 says and it's sense 1 out of all the possible accompany VBs that exist in the database. Okay, so score NN2 is like the second sense there. So that's like the final sort of output we want, which is kind of a common thing that people work on, just to say like they want to do things like show me flights from Boston to New York, and like turn it into a meaning representation, so that then you can use that to actually answer the question. So this is kind of the motivation for doing this thing. So basically what we want to do is use our knowledge that we've learnt about the database to solve this task. So let's skip that one. So yeah, so we can do that by, I mean, it's almost in the right form for us already, because after we've done the semantic role labeling and we have like the triples like this, notice they look kind of quite a bit like the WordNet triples that we were training on. So, like the car has part wheel, it sort of looks a bit like this. It has like the relation in the middle and the two, concepts on either side, except WordNet doesn't cover all possible verbs. It only has 18 relations in here. But still, the idea is, if we kind of train on this task and we use like the WordNet training and we multitask them so that we've used WordNet to learn about the world, can we improve the disambiguation of grounding this thing? So yeah, that's basically what we did. And so we have a model that basically just predicts the sense of each, just goes through each entity in the triple and tries to find a maximum scoring sense using a neural network. And yeah, it's it's exactly the same model basically as before. But so yeah, what we're going to do is we're going to take WordNet and we're going to take unlabeled text as well, and then multitask those things for that task. So just like before, we have like one embedding vector for each concept, one embedding vector for each word, and we train then that network that takes the left-hand side, the relation, and the right-hand side, and predicts the score. And we're going to choose the disambiguation that gives the maximal score. So yeah, there's a little trick how we build the training data. Like, we call this unambiguous text. So what we did here was we took unlabeled data, and we did like the part of speech tagging, and once you get to a company VB within unlabeled data, if that thing is unambiguous in WordNet, so there's only one sense of that, then we kind of already know the sense. So then you can, it's a bit of a trick, but then we can go to the what's called a syn set in WordNet, which is like the set of all words that have that same sense, and we pick another word from that syn set and we put it in the sentence instead, which might not be exactly correct, but then we kind of know for that word, which might be ambiguous, we know the true sense of that word because it should be the one from that syn set. So we kind of generated like data in that way. So, because otherwise we don't have so much labeled data for this task. So we did that, and so I should say the test set here I'm going to show is called extended WordNet, which is basically sentences that have been labeled with these senses in WordNet. So that's we can use that. Yeah, there's 5,000 examples from that, which we use as a test set. So after we train this whole model, we can evaluate success on that. So basically, our model, we tried it with different different subsets of training data. So this multitasking that we're doing, if we use basically only WordNet, then we get 29.55 F1, which isn't that good. If we add like the unlabeled text, we get a bit better. And then if we throw in like everything, so that's with the unambiguous text and the extended WordNet as well, I guess, then we get pretty good, like it's 67, or it's a lot better than what we had anyway. But actually this MFS, this is the bad point. The MFS is the, if you pick the most frequently occurring sense, and just predict that, which is like a really dumb baseline, actually you already get to 67, so it doesn't look so good from this point of view, but our models didn't really take into account the frequency, that most frequent sense, very well. So if you actually add that into the model, then that's this all plus MFS, then you get up to 72. So this then is actually a model that's doing something. I mean, it's actually disambiguating. So we didn't really compare to anything on that data set, but on the SensiVal 3 test set, so this is was a competition, I think, where there's, I think this was the winner of the competition, actually, I'm not sure. But this is on some subset of the test set, I should say, where we could extract these triples. Then we can compare our method to that, to Gamble. And if we do this all plus MFS trick, we have the best result that we know on that subset of the test set. So we're doing okay. And basically, just by having this trick of multitasking all these different types of knowledge and putting them in one neural network to do the disambiguation. So So what I'd really like to do is do that thing. I mean, if you look back at the universe thing where I was grounding an actual simulation, I'd like to do this kind of larger scale thing with lots of concepts in the real world simulated environment, but it's sort of harder to collect this data. So that's kind of like why we went off and did these experiments instead on WordNet. So at least we could say, look, this kind of model, it works with lots of concepts, lots of words, and quite well compared to other methods. But yeah, I think it'd be pretty exciting to try and do that in a kind of a real environment, like with a changing graph, whereas WordNet is fixed. And yeah, so this was just to show yet more embedding examples. So you can, because this network takes the three things, what you can do is fix two of them, like the left-hand side and the relation army attacks, and you could rank all the concepts that would most likely to appear on the right-hand side. So you get like troop, armed service, and so on. And then you can do things like, check how that changes if you change just the relation or just the left-hand side, and see that you get nice semantic things from that. That's basically it. That was a framework for open text semantic parsing that actually worked on large scale data, 3.5 million training examples, and thousands of concepts. I would like to try and do that on situated text instead. I guess I'm a bit early, but maybe people have questions.